I am so grateful to have Dr. Olivier Husson join us today on A Regenerative Future. He has been a mentor for me. He has opened up an entire new world for me. He's guided John Kempf, all these people all over the world, because he's written fundamental journal and research articles that have changed everything. So get ready, because this is going to be amazing. All right, here we go. How are you?
I was working the paper with John. We will submit the revised version very soon. So,
wow,
yeah, that's a huge paper.
Wow,
huge one.
So he's doing like field work and research and giving you data.
It's a review paper with many colleagues, but by the way, John is associated to this, and then it explains all the different EH/pH condition for the different pathogens, the different EH/pH condition in the plants, the impact of the stress, and all this interacts and make plants sensitive to disease.
Yeah.
So it's a huge work. The first draft was accepted with modifications, and we are working on the revision. So it should be hopefully maybe at the end of May, maybe we will have it published.
Wow, that is amazing.
It's a huge one.
Thank you.
It's a huge one. It's really.
Oh wow!
It's a huge one, really. It's I think there's something like 450 publications in the review, but I started from something like 5,000.
Well, yeah, I know how that goes. It's quite the
Thanks,
space.
COVID.
It's quite the space when you get into it, and it's humbling. For me, I came from the gardening space, and people who are gardeners tend to talk like they know things. And they don't. And so it's really important to be humble and to do a lot of reading.
That's called the Dunning-Kruger symptom. You don't know. It's American doctors who published on this, is that when you don't know something well, you think you know it, and you talk with a lot of insurance, and you're very, very sure of what you're saying. And the more you learn, the more humble you get. So I think it was in the 70s. It's two American doctors who did this study. So.
Well, hopefully the work that I do will bring more complexity, more humility, more reflection, and connect people to information and researchers like you and like John, because it's so important that we do this research. And one of the questions I wanted to ask you is, where did this all start for you? How did this begin?
Well, it's multifactorial, I would say. It's a combination of different things. But in France, we have a kind of training for agronomists. First, I'm engineer in agronomy, so it's a kind of training where it's rather balanced. You have a lot of physics, a lot of mathematics, a lot of biology, a lot of chemistry. So it's a competition. You after the bachelor, you have 2 years to prepare a competition, and then only the top one gets access to the school.
Okay.
For engineer in agronomy. So already I always liked physics. And then I've been working most of my career with Lucien Segui, he passed away just 1 year ago, was an agronomist who worked a lot on conservation agriculture in the tropics. And it was the same. We worked a lot on designing cropping system with farmer based on conservation agriculture, and developed the principle and understanding the cover crops and all these things, the importance of having them. And I did after being engineer in agronomy, I worked in Vietnam, and I did a PhD in Vietnam on soil that are very specific. It's called acid sulfate soil. It's soil when they oxidize, they acidify, but they really acidify. That means that locally you can be at pH 1. Okay. In these soils, you have up to 3% of pyrite, it's FeS2, and 1 mole of pyrite that oxidize produce 4 moles of sulfuric acid. So at that time, I've been working on rice a lot, and rice can be in water or in upland. But at that time, I've learned the redox chemistry for paddy field. It's very well known. And then 20 years later, working on cover crops and all these things, I thought we are missing something. To go further, to improve our system, we need to understand that's something we don't get well. So I thought, why redox chemistry is so important in paddy fields, and we never discussed this in aerobic field. Why? What's the main reason is that we don't know we didn't know really well how to measure, and it's not the same redox couples that are at stake. So it seems less important, but in fact it's maybe even more important. Especially it leads me to understand that the key point in the soil, it's the soil structure, because this will impact very, very strongly the EH and pH in the soil. So all the solubility of the availability of the nutrients, the toxicities, all this is related to the soil structure. And the plant, they know this, and the microorganism, they know this. So the plant will use microorganism and macrofauna to improve the soil structure. So the plants, they will feed the macrofauna and the microorganism to improve. One of the roles will be to improve the soil structure and to buffer EH, pH in the soil to make it more balanced, to have the nutrients available and all these things. So that's really a key point. And quite often on redox, people say our soil are too oxidized, but that's not the really correct thing. Our soils, most of our soils have a poor structure. That means as soon as it's raining, with water filling in the pore that are there, there's no more oxygen, so it's too reduced. And a few days later, it's drying again, and it's too oxidized. So the plants, they always shift from too reduced to too oxidized. There's no buffering, or for redox, we call it this poising capacity. But the thing is that if you don't have a good soil structure, EH and pH, they go, EH in 2 days can go up or down by 800 or 600 millivolts. So in fact, you need a good soil structure to have, and also in a compacted soil, the EH and pH are rather homogeneous in space. There's no diversity, there's no EH, pH niches for microorganisms, in fact. So, but all the soil is at one EH, pH level with very little variability around this. And it changes very fast with time. So this is very bad for microbial activity, or for life in fact, because for 2 days, then only the anaerobic microbes will survive and can develop. And then 3 days later, they all died, and it's another population that tries to develop. And when you have good soil structure, it's the opposite. You have little variation in space, in time, but you have a huge diversity in space. And this diversity in space, it selects, and it is selected it is improved by the microorganism. So you can have huge biodiversity because you have different EH/pH condition favorable to different microorganisms, and to have all the cycles of the nutrients working well, you need different microorganisms that function at different EH and pH. The nitrifying bacteria, they work only at high EH in oxidized soil. The opposite, the bacteria that fix nitrogen, they work only at very low EH. So that's also the importance of the soil structure. Within an aggregate, you have a huge variation on EH and pH. Inside the aggregate, when there's more humidity, it's lower. There's less oxygen. So there you can have nitrogen fixation. When you have a compacted soil, you have very low diversity and it's changing all the time, and the cycle cannot be filled in.
So that makes, all right. So in my mind, when I think about structure, there's these like influences and schools of thought that come in, and then I'm always trying to kind of fit them together. And so the structure is also the differentiation of pH and EH. It's not just physical, right?
Yes.
The differentiation creates the charge difference.
And in fact, the chemistry impacts the biology, and the biology impacts the chemistry. Mm-hmm. And it's the same for physics. John says that it's physics, that it's all interlinked. In fact, the plants, they will modify EH/pH in the soil and make structure through the roots that will help, that will select, that will recruit different microorganisms. And this microorganism, once they start to develop, they adjust, they change the chemistry to adjust it to their optimal level. So the chemistry, EH/pH, is impacting the population of microorganisms, and the population of microorganism has a strong ability to impact EH/pH. And the plants, they will use this, they use the microorganism to make different EH/pH niches in the soil, so that they will have access to all the nutrients, all the cycle will be filling in a good way. At the same moment, you need to have a balance between nitrate and ammonium, for instance, if we talk about mineral nutrition. But in a soil which is not, all the plants, they work better when they can absorb both forms.
Yeah, I was thinking about that recently, because it seems like they prefer to be in that ideal zone because they have pivot power. They can lean this way and grab this. They can lean this way and grab that, right?
Yeah, there's this, but there's also the fact that the plant that absorbs nitrates, NO3 minus, mm-hmm. they get alkalinized a lot. And the plant that absorbs ammonium and H4 plus, they get acidic. So they acidify the rhizosphere, or they alkalinize the rhizosphere for nitrates. And they have to do this to keep their charge, but also because in ammonium there's a lot of H plus, and in nitrates there's a lot of oxygen that with water will give OH minus. So all the plants, they work better when they can absorb both forms. Okay, absolutely. And in a compacted soil, they can absorb only one form. But for a few days, it's one form, and for another few days, it's another form. So they get too acidic and too alkaline, and they shift all the time, and they spend a lot of energy to buffer the pH in the plant. So, in fact, to buffer the pH in the plants, it's proton ATP pumps that works, and to make this pump works, you need energy. So the more these pumps need to work, the more you oxidize your plant. So a change in soil EH, a change in soil pH, the plant will sustain a pH, but it will cost a lot of energy. So doing this, you don't really see a change in pH in your plants, but in fact, the redox is going up. The plant is losing energy to adjust the pH. And when the plant cannot adjust the pH anymore, it's getting really complicated.
Mm-hmm. And that's when all the bad things happen.
So it's all in interaction. So 20 years ago, everything was related to pH in soil, in plant physiology. Globally, all the microorganisms, they breathe. So they take oxygen and they release CO2. Okay, so this CO2 is vented in the atmosphere. CO2 is the most oxidized form of carbon. So globally, microbial activity, fungi or bacteria, it's lowering redox potential because oxygen is getting out of the system through CO2.
Wow, that's really good. That's perfect.
It's always the difficulty to understand this redox, like entropy. Which system are you looking at? And it was I did not mention, but my brother is working on private consultancy on fish farming and shrimps farming, and working with redox at the same time. We went together developing all this. And there was one thing we could not agree for a long time. He was saying that photosynthesis was oxidizing. And I said, no way, photosynthesis is the primary reduction. So there's no way photosynthesis is oxidizing. But photosynthesis is reducing the plant and venting, or the soil, and venting O2. So when you measure your soil with the root exudate, and you see it's a decrease. But when you measure in water, you have more oxygen in your water. So photosynthesis by algae, they oxidize the water. So you always have to look at which system you're talking about.
Yeah.
You need to get perspective, you know.
And in Vietnam, in that setting, were you close to the water? Were you close to where that shift would be happening?
Yeah, we were in the Mekong Delta. So for 6 months per year, you had the Mekong River with the flood, flooding everywhere. So pH was going up, redox was going down a lot. And then at the end of the flood, as soon as the soil were getting on the air, not underwater, you had a huge acidification. It was crazy. The difference in altitude in the field, you had tremendous correlation with the yield.
Wow.
We had some fields where we had more than 700 kilograms of paddy per hectare per centimeter difference. That means you were going up 1 centimeter, you could have 700 kilo per hectare more.
So how are you successful? Like, how does one succeed in that kind of circumstance?
It was kind of crazy. In fact, this stupid Vietnamese farmer, nobody told them it was not possible to grow rice there, so they grew it. So now, in fact, it's to give you an idea, we found the technique. We need to adjust just according to the elevation of the field. In fact, it was the plain of reeds. It was the end of the Ho Chi Minh Trail, just near the Cambodian border. And we were 140 kilometers from the sea, and the highest point I measured was 1.1 meter above mean sea level. Okay, so it's flat.
Yeah.
But within a few, let's say, all the fields were between 65 centimeters above mean sea level and 1.1 meter above mean sea level. But it was between 85, around 85 centimeters above mean sea level. Everything was shifting completely. Below this, most of the time you were too reduced because of the Mekong River.
Yeah.
And above this, most of the time you were too oxidized. And the vegetation was completely different. Within a few centimeters, it was completely different. So when it was too low, you had Eleocharis dulcis reeds. And when it was too higher, it was grass, Ischimum rugosum. So for farmer, we just told them, okay, if you have mainly the reeds, you have to delay the planting and pump water out of the field as much as you can to oxidize. And if you have mainly the grasses, then do the opposite. Plant very early, and pump water as much as possible in the field.
Wow.
So that was quite successful, because in 5 years we reclaimed 120,000 hectares of soil that were supposed to be impossible to cultivate. And first we started with 1 crop per year, and after 5 years we shift to 2 crops per year, because we were improving the possibility to regulate water in this field. And so the total was something like 1 million tons per year of rice produced in this area, starting from nothing in 5 years. So,
wow. And it's healthier rice too. I mean, this is rice that's it's healthier rice too, right?
Yeah. Also.
Healthier plants, healthier people. I love it.
Yeah. Rice grows in too reduced condition. You can have arsenic toxicity in it.
Which is increasingly common.
Yeah. But you have shrimps, you have rice. It's arsenic is more soluble when you are very low redox potential. So, but the good thing with rice, I spent most of my career working on rice, is that rice can grow in paddy fields underwater. Even in some places in Vietnam, you could have rice in more than 2 or 3 meters of water. And just moving up with the flood and then going down. But it can also grow like an upland crop, like any crop, like wheat. So for redox, working on redox, you have all the situations. But what is striking is that when you get reduced, iron is the key element that will affect EH and pH. Okay? So you have a lot of iron in the field, in the soil, and iron for nitrogen. Nitrogen is exchanging 1 electron for 1 proton. That means you have a constant oxidation level. Let's say P plus pH. But iron, it's different. It can exchange more than 1 electron for 1 proton. So the natural trend between EH and pH, when you deal with nitrogen, and it's what you have mainly in aerobic soil, there's no big shift in this. But when you are in reduced condition, it's iron that will get more important in the redox reaction. And then you have a very strong drop in EH and only a small rise in pH. So that means you really enter into anaerobic conditions. And so it's one important role of this transition metals, is that they exchange different number of electron and proton. So they have redox reaction at PE plus pH, which is not constant. So that's the very strong ambiguity with redox, is that oxidation has 2 different definitions. Mm-hmm. In electrochemistry, it's the loss of electron. But in organic chemistry, it's the gain of oxygen or the loss of hydrogen. And it's not, you don't read it the same way on a EH-pH diagram. The official definition, loss of electron, you go this way. increase in oxidation number, you go this way, and gain of oxygen, hydrogen, you go this way. But all this is called oxidation for the science of for electrochemistry. And then, so they say organic chemistry, it's more oxygen and hydrogen. But then they say that a gain of oxygen is the loss of 2 electrons, the loss of proton, and a gain of OH minus. And they show the reduction of methane. But when you gain oxygen, you lose electron and you gain OH minus. You alkalinize. So that's
okay.
we need to work on this. That's an important thing, is that nitrogen, you exchange 1 electron for 1 proton, so you don't shift too much this Pe plus pH.
Yeah, thinking about like the red soils of southern United States, if they're bringing their soils down into how reduced would you say do they need to start paying attention to this? And what would you recommend they do in that context?
The problem is that when we measure soil EH, what do you measure?
Right.
You measure an average EH level, and you can be exactly at the right level, but very temporarily. If your soil is compacted, you have what is important is to see the variability. You need to have an average level, but more important than the average level is the buffering capacity and the variability in space around this level. And this you cannot measure with what we have available at the moment. So there's a huge variability between, and in the rhizosphere, it's completely different. It's probably as soon as you get anaerobic, let's say, the problem is that real anaerobia is not related to EH, it's related to Pe plus pH. It's not straight on this EH. It's oxygen versus hydrogen. So let's say Pe plus pH above 9 or 10, you get microtoxic, and above 14 you are in oxic condition. But anoxic condition is below. So let's say at pH 7 it would be something like EH 200 300 millivolt. I have to calculate, but 7, I told you 10. Yeah, around 200 millivolts at pH 7. So below this, you get really anoxic. But the plant is at low redox. The plant is making the photosynthesis and is not at the same redox level than the soil. It brings energy to the soil. So an average level for the soil, good average level is around the electrical neutrality, so P plus pH 7. That would mean at pH 7, redox around 400 millivolt. But you need variability around this. Okay, but a plant, it depends on the species, but it would be something like 200 millivolts lower, because it's the plant who brings all the energy to the soil. And it's another problem of getting this anaerobic condition in the soil, is that you have electrical differences, and it creates strength. When you have a positive and a negative electrode, the electrical charge, they will move. So the minus will go to the plus to the minus will repel the minus. So in a normal system, when you have the root at a lower EH than the soil, you are negative on the roots, positive on the soil. Okay, so all the negative ions, all the anions, they will have difficulty to enter. They will be repelled by electric force. So nitrate will be difficult. So the plant will need to mobilize pumps to fight against this electrical gradient. So it costs energy to the plant to absorb nitrates. But when you get too reduced, it's getting the opposite. It's the ammonium that will be repulsed. So that's another shift in the soil. When the soil goes below 200 millivolt, the plant has difficulty to absorb nitrate. There's no more nitrate in the soil. It's mainly ammonium that is present in the soil, and ammonium is positive. So it's the root is more positive than the soil. So you have a force that ammonium absorption, nitrogen absorption decreases when the soil is getting too reduced, whatever the plant, even for rice. The microbe will try to buffer their environment to the optimal zone. Okay, but for this they need to be able to develop, and it's the population. It's not one small microbe that will do everything. It's the biofilms. So below the biofilm, you have huge gradients of redox, and each population of microorganism will adjust its environment to their optimal level. But it costs them energy also. So that's why also they need the plant to feed them. They will use root exudate to adjust this. And higher organism, they control redox internally in the cells and externally, the plant in the rhizosphere, especially. But microorganisms, they are too small to control internally. So they control the environment through the populations, and they have a very high ability to do this. They are very strong in doing this. So the plants, they use this strength. They first oriented EHPH to the favorable conditions of the microorganism they want to, they need. Maybe it's because they need more phosphorus or more manganese. It's really specific. They are able to favor different microorganisms according to their deficiency, to their stress. So they adjust EHPH in their rhizosphere. They feed microorganisms, so they will favor some microorganism, and they feed this microorganism with different root exudates, and then the microorganism will buffer and the EHPH level at this favorable environment. But it's the root will not want to have homogeneous EHPH all around in all the rhizosphere. The tip, the apex is it's more acidic, more reduced than higher in the root. So there's some gradients in the root. So young roots, old roots, all this is different. They will favor, they will recruit different microorganisms.
Oh, wow. So that means that the differentiation, people are like, oh, well, it could be different every root hair. It has to do with redox, and it has to do with the newness of the root, or like the area of the root, how new it is, right?
Yeah, you have a root is like creates an electrical field, in fact. Between the apex and just above, you have different redox level, and this creates an electrical field. And the zoospore of omicets, they are specifically able to identify. Some will go to the cathode, some will go to the anode. And when you have when the root is damaged, you create different electrical fields, and it can attract Phytophthora, for instance, will go to different parts as compared to Pythium, and it's really specific, and it's attraction by an electrical field. So So there's plenty of electricity in all this.
Yeah, I feel so. What I've been taught and what I've heard people say is that it's kind of like willy-nilly, and this is so great to have this information because it really organizes our understanding.
Yeah, that's and there's one principle in ecology that says that the more homogeneous an environment, the more the selection will be stochastic, will be random. That means when it's very homogeneous, the selection of the microorganism is just random. Okay? But when the more you have gradient differences, the more it is structure, in fact, the more the selection gets deterministic.
So this means that when the rhizosphere book I was talking about before with you, that when they're like, oh, at first the mucilage and the exudation is all generalized, and then it becomes specific later on, it's more contextual because the plant doesn't have any redox differentiating because all the roots are brand new and there's no root hairs really to speak of.
But you have, you know, James White, you know, but don't forget that, in fact, the microorganism in the rhizosphere, they are related to the microorganism in the soil, to the root exudates, and also at the beginning to the microorganism that were on the seeds. Because the microorganism on the seeds will orientate the condition of the root seed of the root of the seeds, and then it will shift all this condition and shift to different populations. So that's also an important part of having seeds that are well produced, well preserved, because the way you dry them, you will alter the microorganism population. And I'm not talking about fungicide or the seed treatments. It can be also something that will impact strongly. So
he's working on a nitrate stain now. I sent him Peruvian corn, unadapted Peruvian corn, so he'd have the endophytes from Peru. And then I also sent him adapted Peruvian corn from California so he can compare the two. And he was doing his work with tomato seeds. So the roots are like super tiny compared to the giant roots of corn. So I hope we get to learn more about the nitrogen fixing endophytes that are being carried through the seeds.
Yeah, there's plenty of. In fact, the more we learn things, the more we realize that we don't know much. And the more we realize that there's so many things we did not know that we did not know. So we are discovering many things. And yeah, this redox perspective, it helps to connect the dots and gain perspectives, and it's just a tool, but it can be really powerful to organize and to structure, and then we come back again to the structure, and you can. That's the interesting thing, is that you can relate to many different disciplines. You can work with physics, with chemistry, with biology, with pathology, with insect specialists, and it's very rich, and it's a good thing.
Crosses so many domains.
Yes, science is too compartmentalized, and 100 years ago it was not like this. I have very old French books. It's called Treatise of Chemical Physics Applied to Biology, and the three are really connected, and it's chicken and eggs. Okay, so the specialists in microorganism will say that it's the microorganism that rules everything, but the chemistry also rules the microorganism, and the microorganism rules the chemistry. It's really chicken and eggs, and it's related. Chemistry, physics, all this is related, and biology, of course, but you cannot separate before everything was physics or was chemistry in agronomy. As I said, everything was pH, and then now it's EH. But in fact, what is important is both. It's PE plus pH with combination of the two. So you cannot say pH is more important or less important than EH. Both play an important role, and it's the same for physics and chemistry and biology. The plants, they use the microorganism, they alter and they use the fauna to alter the physical structure, and the physical structure will change EH and pH also through structured water, and I think like Polax is presenting. So we're connecting many things. Yeah? When we say we need low PE plus pH to have healthy plants or healthy organism, if you think about it, when you measure, you have something with a lot of proton and a lot of electrons, in fact. But this structured water, if you look at the easy water, it's a lot of electrons. And inside this, on the other side of this exclusion zone, and especially in the tubes, you have a lot of protons. So you have this gradient of energy, and you have this physics also structure the thing, and then you have all the waves, the vibrations, and all these things. It's everywhere, in fact. Do you know that tomato plants, they release the pollen at a special frequency? When there's a special frequency, it's in fact it's the frequency of the insect that pollinates the bumblebee or thing like this. I don't remember the exact number, but it's a very precise frequency that makes that the pollen is released by the tomato plants, the body electric. Yeah, it's so the vibration of the wings of the insect just make the pollen released.
Wow!
You can find videos of this on the internet. Bumblebee tomato pollen frequency, and you will find this. It's amazing.
Oh, wow.
So
that makes me think that if the world's soils have been damaged and we've been abusing and tilling our soils and making them more oxidized, then that would functionally mean that the earth, the soils, are lacking energy, right? That we've removed the energy potential from the earth.
We remove the organic matter, all the carbon that gets the electron.
Yeah.
So it's an electrical system. So it's rather simple. You have the solar panels. It's the leaves. They load the battery. It's the soil. Okay, and you can say that the very stable carbon is the structural part, is the compartment of the battery, and the the biological activity is the load level of the battery, how much it's loaded. So it's the EH, it's a voltage. Okay, and then the production of your system. It's the power of your system. So the power, it's a voltage, square voltage divided by a resistance. So in agriculture, we use more often the conductivity, the electric conductivity. So square redox time a conductivity, you get the power. So it's the production level. So in fact, what happened, I believe, is that if you reduce the resistance, you produce more. The power is increased, you produce more. So it's what we did with chemical fertilizer. We increase the electrical conductivity, so we increase the productivity of our system. But at the same time, we unload the battery faster. So if we don't have all the solar panel to reload the battery, then you are emptying a battery.
Yeah.
Okay? So it's what happened. In fact, we have emptied our batteries, and that's why most of the time talking about conservation agriculture is not enough anymore. We need regenerative agriculture. We need to reload the batteries. To reload the batteries, you need carbon, and to get this carbon, you need plants, because all the energy is coming from the solar energy that plants transform into chemical energy. So again, it's linked. It's physics, radiation, that's biology transform into chemistry. It's
so what do you think? What do you think of, Elon Musk's challenge for someone to figure out some way to draw down all the carbon, or someone, lots of people have these challenges and these are also the same people looking for batteries and energy. What do you think about all that, given this information?
Well, I'm not aware of all the things that Elon Musk is doing, apart from sending a French astronaut in the space station a few days ago. But I think there are some risky things in what he's doing. So, but anyway, there's different ways. But
what I mean to say is, in my mind, it seems so silly to be offering these big cash prizes for some way to sequester carbon when it's very clear that photosynthesis can do it the best.
Yeah, and with free energy, it's the solar energy, free. And don't forget that to get a solar panel, a physical solar panel to reload your cell phone or something, or to make solar panel plants, you need rare earth, and this is not infinite. Mm-hmm. While growing plants, you can have them. You don't need any specific metals, or so this is sustainable. And the energy is free. We have this solar energy which is free, and it's free when you have a plant intercepting the solar light, the solar energy, you get a reduction. Okay, but if you let the ultraviolet reach the soil, then you have, again, iron, manganese are fundamental in redox chemistry because they are involved in what called Fenton reactions. And the ultraviolet of the sun reacting on iron, they produce a very, very oxidizing element. Okay? So if you have a plant, you are reducing your environment. If you don't have a plant, if it's bare soil with iron, you are oxidizing, strongly oxidizing. Okay.
So that makes me...
There's some complicated loops in redox chemistry. In Fenton reaction, they have been really overlooked in the functioning of the soil. And there are recent publications showing these things by Kuzyakov, especially. Very recent publication. It's fascinating because the first publication on this was saying that it's very marginal. It contributes to oxidation to mineralization of very limited amount of organic matter in the soil, and it works in the desert, in the Atacama Desert, where you have almost no carbon, but you have chemical attack of this carbon by the Fenton reaction by products. And the less organic matter you have, the more you have this reaction. Okay, so first it was said that this is limited to this to special situation, and it was in a normal soil, it was less than 1% of the mineralization and things like. And the recent publication, they show that the more iron you have in your soil, and more important, the more period of anaerobiose and anaerobiose, the more you get this Fenton reaction. And in the tropical forests on soil with a lot of iron, it can be 30 to 50% of the mineralization.
Whoa.
Just chemical attack of the organic matter by the product of the Fenton chemistry.
Oh, wow, that's really
so that's very new thing. It's very recent publications a few months ago. So there's plenty of things we overlooked, and the knowledge is increasing. The difficulty is to get access to all this knowledge and to structure this, and that's the good thing with this Redox perspective, is that you're connecting things. You can talk about entropy if you want. You can talk. There's plenty of disciplines that can interact, and it's fun. It's a lot of fun.
I see it as a linchpin lens that allows us to view things a different way. So thinking about that we've had the Fenton reaction happening, we've been tilling, we've been exposing soils and then abandoning them for thousands of years. What in your mind, or if you've thought about this or not, the primeval, like the wild soils, what were soils like when we had these tall canopies on the earth? And how did things function differently because of that?
There's probably a climax that was reached with the more organic matter you have, the more mineralization you have too. So at the moment, you reach a climax. You don't need, it's very difficult to get more organic matter than this. But what's important is this soil structure. And this is also something that research is working on, very interesting research in Switzerland, for instance. They relate the soil structure not only to carbon, but to the ratio carbon by clay. That means if you have 10% clay, you need about 1% carbon to have a correct structure. Okay, but if you have 20% clay, to get the same structure, you need 2% carbon.
Oh.
That means 3.4% of organic matter. And if you have 40% clay, like in my garden, 40% clay, you start getting a good structure when you have 4% of carbon. 4% of carbon, it's almost 7% of organic matter.
Wow.
There's not so many soil with this. So I'm bringing organic matter to my soil. But that's an important thing. Thinking about ratio clay carbon or carbon by clay. Okay.
What are our crops we should, because I mean, it really depends on the soil types, right? because some farmers are going to want to switch right when they learn about this. They're going to want to switch. But how can they really know? How can folks know where their EH is for their soil?
For the soil, it's not useful to. First, it's easy to look at the weeds you have.
Yeah.
Okay? And we developed an application where we have all this in French, but you make a diagnosis of your soil based on the weeds that are growing there. But the worst is the soil where you have plants that indicate oxidized condition and other plants reduce condition. That means that it's fluctuating all the time. It's this compacted soil. You have plantago and different plants like this, but it's not really difficult. It's just compaction. If your soil has a good soil structure, the redox condition will be favorable. Because to have a good soil structure, you need carbon, you need biological activity. And if you have this, you will have a good soil EH, pH characteristics with different ecological niches, and it will work. If you don't have a good soil structure, then you can measure EH, pH, because pH in 3 months in the soil, in the bird soil, can change by 2 or 3 units.
Wow.
So it's just you get water above the soil, then the reduction links to, especially to the iron, will make that pH will raise. Redox will go down, pH will raise. Okay, but then you need to look at the rhizosphere. What's happening when you are at low Pe plus pH, where you will have ammonium mainly? The roots absorbing ammonium will release a lot of protons, will acidify a lot the rhizosphere. Okay? And then when you acidify the rhizosphere, you make aluminium soluble. That's a problem you have in many pastures that are compacted, where when you look at the soil analysis, there's not so much aluminum in the soil. But when you look at the forages you grow on this, it's loaded with aluminum. It's probably because waterlogged conditions leads to acidification of the rhizosphere by the plants who absorbs ammonium, then release H+, that solubilize aluminum, that's enter into the plant.
That's why it's so important to have that plant sap analysis testing that John is focusing on.
Yeah, and you can have the opposite. That means a lot of manganese in your soil and no manganese in your plant because the soil is too oxidized.
Ha!
And that's so it's important to understand all this interaction and the dynamics in all these systems. And when it's fluctuating all the time in your soil, the plants cannot get in good conditions. It spends too much energy just to buffer the pH in the cells, and remember, as soon as you have differences in pH, when you have unbalanced pH in your soil, the plants will spend energy to balance this in the cell. So it's getting more oxidized, and all the energy it spends adjusting the pH internally, it's not available to make new leaves. Okay? Yeah. So it's a vicious circle. You spend energy to compensate for the environment, which is shifting all the time, but globally you oxidize the plant all the time, and the plant spend energy that is not available to make more solar panel, more leaves. So it cannot acquire more energy, and it's a vicious circle. It's the degradation circle.
Yeah.
That's why it's so important to boost the photosynthesis at the beginning.
Right, and give them enough space so that they're not shaded out.
Yeah, because it's the plant that will correct the soil structure through microorganism and through macrofauna. It will feed the macrofauna, but if you don't have the plant to feed the macrofauna and the microorganism, the soil structure will not improve. How do you call it? Inoculating with microbes will work only if you feed them. So you need the plants, you need the organic matter to feed all this. Otherwise, it will not work for long. It will be very expensive and not efficient, because you need to feed them.
Absolutely.
And provide them with conditions that are favorable for them. If you apply this on very compacted soil that will get very dry for 3 months, they will die.
Yeah.
Even if there's some food for them, you can bring sugar. That it's not enough. So you need to provide them with rather correct condition, and it's chicken and eggs. You create rather correct condition, they will improve the conditions. And so it's the question is, how do we start this virtuous cycle of regeneration as fast as possible? It's the important point. You need to go rather fast, otherwise it's getting very complicated.
Yeah. So speaking of testing paramagnetism, are you using the Callahan meter or are you using something else?
No, I was just talking about this. It's been a few years. I've been looking for funding to be able. I have this field Callahan soil meter.
Uh-huh.
I'm not going to say like John. John said that he had it on his chimney for a few years and then get rid of it. I'm using it because not for measuring paramagnetism. It gives you a broad idea. But so for your soil, but you cannot do research on this on the soil with this. It's really an order of magnitude. It's just give you an idea of where you are. But
okay.
I'm using it because that's something. The measurement of redox potential is polluted by electromagnetic field. Okay, so the main point is, where do I measure? When I measure for plants, for instance, where do I stand to measure this? And it can be even in a field. 2 meter differences, you can have very good measurements that will replicate, that will reproduce, that will be, you will understand things. You move 2 or 3 meters on the side and you get almost random results and you don't understand anything.
Wow.
And in fact, this field Callahan, you need to set up the zero, okay? And there are some places you cannot set up the zero. You turn it, it's zero, then you take your sample, it's not zero already. And when you are in such a place, measuring redox is just meaningless. It's just something empirical we discovered. But so I'm using the field Callahan meter to select the places where we can measure redox properly.
Wow.
This is the past, I would say. We are calibrating this kind of tools. So this is a prototype.
Okay.
So it's a startup that designed this. In fact, it's infrared spectrometry.
Oh.
Okay. So we are calibrating. So now with this, we are able to predict the measurements for pH, electrical conductivity. We are calibrating for bricks, and we are trying to see if we can do micronutrients. Within a few weeks, we will know if it's possible for rapeseed.
Wow.
So this is calibrated. This is calibrated. You know, for the moment, you look, see, it's prototypes.
Oh, it's science. Oh. That is so cool.
There's very few available, but anyway, it's classical standard spectrometry. So just a cell phone, you have it here. So it's Bluetooth to the cell phone, and then you have an app. You just scan, send the scan, then connecting to the application will just tell you say, okay, it's wheat. You scan and it gives you EH, pH, EC in a few seconds. So that's a revolution.
Yeah.
So yeah. We are working on calibrating this year for corn, green salad, tomato, potatoes, grape wine, rice. But we use this, and then we have deep learning. Okay, Sensing, this company, as specialist in deep learning, and they improve the prediction of the measurements. It's incredible. We have R square of 0.95 now. And the standard deviation of the measurement we get, it's the standard error is around 5 millivolts for redox. It's when you get 5 millivolts with classical electrochemistry, which, let's say 2% in one day, we can measure 30 samples. Okay. Mm-hmm. And 5 millivolts precision, you are really, really good. And with this, we have it. You don't need to calibrate things. You don't need to set up you arrive, you scan, you have your result. End of the day. So it's changing fast. It's so this year, and there's been there was a crowdfunding campaign in France, and that's how we got the money to calibrate for these new crops. So
I have great hope for AI, actually. I know a lot of people are scared of deep learning, but I have great hope for it because it has this ability for us to show. It feels like a way that people trust a lot of the data more because of AI and because of the deeper learning can demonstrate its efficacy at such a symphonic and grand level almost.
Yeah, it's when you look, this is a classical near-infrared spectrometry, but when you look at the classical way for prediction, we get R square of 0.7. When you enter deep learning with neural network convolutions learning, and in this, it's 0.9, 92, 95. And so we get this with about 1,000 samples. Huh. So that means we need 1,000 measurements with classical methods. So that means something like 30 days of work. And then we have this. So it's coming soon. We will receive 50 devices. So for the moment, it's priority for the people who are calibrating them.
Yeah, of course.
But next year it will be available. Yeah. So,
this is a great hope for many people. This is amazing.
Yeah, for farmer, it changed completely. The thing, measuring with electrochemistry, it's tricky. You need to know how. It's very long. You cannot do it. As a farmer, you don't have the time to spend one day to make 30 measurements. Okay. Now with this, farmer can just go in the field at 11 in the morning when photosynthesis is working well, because early in the morning the plant is more oxidized, so you need to wait for the photosynthesis to start it. Then you just scan 10, 20 leaves of in your field. It takes you less than half an hour, and you know if you risk disease or not, or if your plant is healthy or not. And if we can get the micronutrients and the nitrogen forms and different things from the sap analysis with the same device, then it will be really a change maker. Within a few weeks, we will know if it's possible with this kind of device to get the sap analysis result at the same time. We are doing analysis for rapeseed for the moment. So if it's not working with this wavelength, we will work with other wavelengths, and we will see.
It feels like in a very short period of time, we're going to have a completely new conversation about how we grow our food because of this.
Yeah. How we grow food and the quality of the food.
So with this device,
the Bionutrient Association, it's the same kind of things behind this. So
with your new
I'm working
paper,
more on the
with your new article, the one with John that you're working on, and those other contributors, that is going to be like the lens that farmers turn to when they get that data, right? So they're going to look at that data and then be like, well, this means, given the research.
Yeah, for the moment, we have the main EH/pH area for the main groups of pathogens, but it's really specific, in fact. And in fact, what's interesting, we need to make an update with John on the training, because it all came from a question of one farmer during this day of discussion. But I said, he asked me a question, where is it? So I had to look more into detail in the plant. In fact, the phloem, where you have the elaborate sap, has completely different EH and pH than the rest of the plant. The xylem is that different level. The extracellular space is the more acidic, the more oxidized, is where you get the fungi. Okay? And in fact, you can really relate the different part of the plants where the different kind of disease can develop as a function of the different stress you can have in the plant. But for instance, most fungi, they develop in acidic condition, especially the necrotrophic fungi. It's very acidic plant condition in the intercellular space. Okay, but there's a few fungi like Coletotrichum that can develop on more alkaline conditions, neutral to slightly alkaline conditions. They have the ability to produce ammonia. So they alkalinize. There's different processes like this, and these ones, they are the ones that can develop in the xylem, which is more alkaline. And if you look at the viruses, they are in the phloem. The phloem is the more alkaline part of the plant. The viruses, they need high pH, and it's where we change a little bit. They need an absolute EH level, which is rather low, but which corresponds to an oxidized phloem. And the phloem is strongly, and the phloem is strongly buffered. So if your phloem is oxidized, that means that your plant is strongly oxidized. Okay, so the first diagram I had, I represented the viruses in more oxidized conditions than the bacteria. But in fact, it's more in the absolute, the plant is more oxidized, but the absolute level of the virus is more reduced.
Oh, wow.
But it corresponds to an oxidized plant, a very strongly oxidized phloem. Oxidized phloem, which means a strongly oxidized plant. Most bacteria, they develop in slightly aerobic condition. Okay. Alkaline, more, slightly acidic, mainly alkaline. It depends which bacteria. Gram-positive, gram-negative bacteria will have different capacity to oxidize or to reduce with glutathione. So that all the processes are, it's another paper we're preparing, but globally, the bacteria, they will develop in an oxidized plant, but they will sustain their cycle in a reduced soil. Remember, balanced soil around 400 millivolts, balanced plants, depends on the species, but around 200 millivolts. The bacteria, they are around 300, pH 7, it depends which one. So these bacteria, they will need an oxidized plant created by to reduce soil.
Wow.
So they can develop in the soil, they can sustain all their cycle in the soil or in the organic debris in the soil, but then they will be able to develop in plants that are too oxidized because of this unbalanced soil condition.
Right.
Fungi are more on oxidized.
Okay. That's good.
Fungi, it's oxidized plant. It's oxidized extracellular space, so it's also oxidized soil. Okay. Soon we will. The paper will hopefully will be released soon. We're working on the revision of the paper, so it will be there.
I'm really excited. For me, I learned so much from your work because, like you said, it affects everything. And one of the amazing things was realizing, we talk about like good foods and superfoods. They're antioxidant rich foods. And now I think of those foods as energy rich foods,
Yeah, that's the way to see it. But to continue with this device to measure for the plants, we will have to measure many plants and to see what are their optimal level. With this, we measure an average level of the plant. Okay, we don't measure the redox in the phloem or in the, but we will need to develop all this database where we can say that when we have a measurement with this saying that P plus pH around 9.3, pH 4.2, then be careful, you can have Phytophthora, or not Phytophthora 4.2, but anyway, the OMI sets, there are very large range of pH. The Plasmoparaviticula, the mildew of the grape wine, it's probably on a very acidic condition. Phytophthora, they're on more neutral to alkaline conditions. Pythium, more alkaline conditions. So the OMI sets are on a wide range of pH. It's
right, but that's when it's more waterlogged, right?
Waterlogging, in fact, will lower the redox in the roots by asphyxia. So there will be also, the roots will be, it's can we call asphyxia or disease? I don't know. But, the root will be at low redox, but the plant, the aerial parts will be oxidized because the photosynthesis will go down. So waterlogging reduces the roots, which makes acidification of the roots, which favors the development of necrotrophic fungi from the soil. And then on the other side, the drying, oxidation, and nitrate absorption will favor all the aerial fungi, the bacteria, the viruses. Okay. This is something we did in the paper. We took back the several review paper on mineral nutrition and plant disease, including the famous book. And you sort this way, and it's getting very clear. Nitrate ammonium, you understand why this favor this kind of disease and or the other one. It's getting very, very clear. When you look at this globally, you don't understand, because half of the time ammonium will favor some disease, and half of the time it will protect against disease, and nitrate will do the opposite. And when you have this kind of charts, then it's getting very clear. So that's all the knowledge we will need to develop, is that when I do this measurement, okay, I have this reading, am I safe, or is it risky? And that's why also we'd like to have the SAP analysis at the same time. That will make it possible to have the result directly and to adjust which one are unbalanced. So this one is like a thermometer. You get the fever, he's sick or he's not sick. And then you can have more detailed analysis with the SAP analysis to adjust where is it coming from. But having this map in mind, then you can better, and knowing.
Yeah. Do you feel that with this information that we're going to be able to pivot soon enough to really make because I mean, soil loss is happening so quickly. People are predicting, terrible things happening with the world's soils and the environment. But I get great hope from the information that you're sharing with the world, because I can see that we can put it back together.
Yeah, and the nature is strong. So if we work with nature, we can go quite fast. The problem is that you have some threshold levels. Once you are below this threshold, it's getting more and more complicated to restore, to regenerate your soil. So there's huge way to improve this still. I'm sure we are at the beginning and we can go. For me, the main research question is how to do this transition as fast as possible and with the less, the more economic return as soon as possible. Below some threshold levels of degradation, soil regeneration becomes really an investment, like you invest in an irrigation scheme or something like that. And it needs to be economically managed as an investment over a few years. So that would require some other kind of organization of the credits of the so. Anyway, the sooner we react, the better it will be, and it's not too late, but it will soon be too late.
Yeah, and it's almost like we need to get this science up front so that we don't do stupid. The politicians don't do stupid things with pieces of information and being like, "Oh, these two go together." Because that happens.
Yeah, there's also a lot of training behind this, and so it takes time. That's the problem. And but the best, there's all the people like John, like there's many private people who are doing this kind of training also, and it's very encouraging. I would say it's helping a lot. There's a lot of research and training done through this kind of people. So that's why this kind of spectrometer, then we can do research with farmers all the time all together, bringing information. And again, with the internet, we can share information as never before. So just put intelligent information, a useful one in the right form, and it can go faster than before. So and for me, I've been working all my career in tropical countries where extension services have no meaning. There are no funds, nobody, so it's almost nothing. So when we see what the capacity we have in some countries, you can expect that it can go fast. It's that's the important thing is that what is proposed is based on profit for the farmers. And I think the best way to push for this system is that to show that it's where you're going to make more money, more sustainable. You are going to spend less and less. A good friend from CIRAD who quitted CIRAD 15 years ago to take back his farm in France and do this conservation agriculture. Last year was very dry year, especially dry year. He has no irrigation, and on wheat he had a much lower yield than usually. So globally, he's producing something like 8.5 tons per hectare of wheat every year, and the neighbor in conventional system are about 80, something like that. Last year he got 6.5, sorry, instead of 8.5 tons, but the neighbor got less than 5. And he says, but when you have almost no cost on what you're doing, you sleep well, no problem. He has very, very, very low costs for his systems. So when you have low costs, the risk is less, and and you earn money whatever the climatic year, at least for the moment.
I feel like that's a big lesson for maybe all business. Maybe America needs to take that in too, because we need that wiggle room to make mistakes, but to own them and learn from mistakes so that we can continue growing in wisdom.
Yeah, that's normally the research is supposed to be there to take the risk, to make the mistakes.
Yeah.
But there's different way for risk aversion. So risk aversion is something for African farmer. It's the key.
Yeah.
So you have to think all the systems in risk aversion principle. So that you need minimum input systems. You need things but for instance, there's many talks about which cover crop should I use on this kind of soil, this climate, this condition of the farm. But just plant 15 species, okay? Every year you plant 15 different species. You will have 5 or 6 that grow every year, probably never the same, but at least it's a risk insurance. Because you cannot be good enough to predict which climate you will get and to say with this level of regeneration of the soil, this cover crop will work better than all the other ones, okay, this specific year. So you just, besides the interest of having a quorum of different crops, cover crops, the important thing is that with different one, it's a risk insurance. It's an insurance against the risk, against the climatic risk. Okay.
Do you feel like we need to return to land races over uniform crops more?
Oh no, uniform crops are not the key. For instance, these friends I was talking about, for wheat, he has 5 varieties of wheat in the same field.
Uh-huh.
Is mixing wheat varieties, and then there's plenty of possibilities after this with all the cover crops. Even if the climate is getting more and more difficult. In summer, you're never sure you get a rain, so to install a cover crop after the wheat harvest is getting complicated. You never know if it's possible or not. Then you shift to perennial cover crops. Alfalfa, growing wheat on alfalfa, it's working very well. And alfalfa, you install it in a different crop, in rapeseed or in peas, and then it grows, and then you install the rice, the wheat in your alfalfa, and the alfalfa will grow again, even if there's no rain.
So when I said land races, in our definition for land races, they are plants that have a great genetic library within them. So when you plant them, there's like small, fat, tall, skinny, dry, and then wet tolerant plants within the land race. And so we see this in India with the chickpeas. We see this in the corn, in the Native American corn in America. Did we lose that with alfalfa and wheat to a degree? By uniform?
Uniform is we uniform many things, but it's
wow, I didn't realize that.
It's diversity against the problem.
Right.
Diversity, because then it will be adapted to the changes in the conditions. You will have one of them, or at least some of them will be adapted. If you just shoot one bullet, you need to be sure that you will hit the target.
Right. Okay? Absolutely. Wow, that is just so amazing. It is 8:11, so I don't know if you have to go.
Yeah, we have to go, yeah.
I want to respect your time. I appreciate you giving us so much, and giving your life. I mean, you have given your life to finding these secrets of the
No,
nature of our world and sharing them with people. This is so important. This is going to help.
I'm having fun in the job. That's the most important thing.
Yeah.
It's having fun, and I think John thinks the same. It's so much fun to when you see the opening doors like this and where you can go and moving on. It's within a few years we learn a lot, and it opened a lot of doors for lots of improvement. And the priority was to develop this kind of device because measurement is the key. And it with classical electrochemical methods, no farmer would use this because he would be right. It's too long, too complicated, to not sure enough to have good results. So it was the priority. We've seen last year that it's working very well with wheat and rapeseed, and for the moment it's the two that are on the app. We are developing them, and it's opening a lot of opportunities, a lot of doors. Yeah, it's
so excited.
Really fun. So
thank you so much.
See, you're most welcome.
Soil is the linchpin to life, to civilization, to health. If we want a healthy future, to fight environmental collapse, to live regeneratively and ethically, and to experience a life of abundance and freedom, we want healthy and abundant soil everywhere. But that means we need to relearn old ways and learn some new ways to build, cycle, and partner with soil and soil life. We can change the world radically, but it's up to us. We have to make those choices. We have to partner with soil and soil life. It takes our participation and support. Will you join us? Regenerative Soil, the full program, we're going to dive deep. We're going to be looking commercial, we're going to be looking DIY, we're going to be going garden, we're going to be going farm scale. We're going to cover it all. We want to serve everyone at all levels, and we want to create that fluency, micro to macro, so that we can spread the regeneration of our soil, our ecosystems, all our systems, all across the world. You can do this. You can regenerate soil, because regenerative soil is the linchpin for life. It's the linchpin for all systems, all of our civilization. Everything is running on this. Everything is based on this. Everything is relying upon this. Check out the link down below. Sign up and join us in Regenerative Soil, the full online course. You're not going to want to miss it. I'm Matt Powers. Grow abundantly, learn daily, and live regeneratively.